Welcome to the first video I'm making for DEC 2606. Today I'm just going to discuss one of the questions in the third assignment, namely question 4, which is an optimization problem using KKT conditions. Now we have the problem right here. We have minimize a function z is equal to x1 minus 3 over 2 squared plus x2 minus a half to the fourth, under the conditions that x1 plus x2 is less than or equal to 1 and x1 minus x2 is less than or equal to 1. Now the first thing we need to do is write these two conditions in a form which will allow us to use the KKT conditions. This means we'll get two functions g1 of x1 x2 equal to x1 plus x2 minus 1. So we want to write the conditions so that we have a less than or equal to and a 0 on the right hand side. We then also have g2 of x1 x2 is equal to x1 minus x2 minus 1, and we know from the conditions that that will be less than or equal to 0. Now from this we can find the Lagrangian function. Now even though we're using KKT conditions here, we have a Lagrangian function in both cases. This is slightly different than it's given in the study guide, but it's exactly equivalent. If we write the Lagrangian function now, we simply update our function with the conditions and the multipliers lambda 1 and lambda 2. We have two constraints, so we'll have two multipliers. Now the Lagrangian, you just write down the function first, the original function which you're optimizing, and then you add the constraints. Now important here, notice we have a minimum problem. So in this case we will want to plus lambda 1 g1. Instead of writing g1, I'm just going to write out g1 and plus lambda 2 g2. Now this is important in a maximization problem. You would use minus in front of lambda 1 and lambda 2. This makes a difference because we assume that, or rather we require that lambda 1 and lambda 2 be larger than or equal to 0. So whether you use a plus or a minus, they might make a difference in the final answer. Now the way I remember this, if you minimize, you're usually using a minimization of a convex function like this, and you're probably not going to get the absolute minimum because of the constraints, so you're going to have to add something to the minimum there to get to the real minimum over the constraints you're using. So you're going to have to add something to move away from the real global minimum. And that's just really a shorthand of how to remember it. What's going on here in terms of convexity and concavity is slightly more complex, but just as long as you remember when you're using a minimization problem, you plus lambda I gi, and when you're doing a maximization problem, you minus lambda I gi. Now we can start looking at the derivative of our Lagrangian function, the partial derivatives towards x1 and x2. So this is just partial derivative towards x1 is 2x1 minus 3 over 2, and there's an x1 term with a lambda 1 in front, so that's plus lambda 1 excuse me, and an x1 term with lambda 2 in front. So that's the derivative to x1, the derivative to x2, slightly more complex because we have a higher power here. We have 4x2 minus 1/2 to the third, to 3 there, and there's an x2 term with a lambda 1 in front of it and an x2 term with a minus lambda 2 in front of it. And then we are going to set these things equal to 0. But we have some more to work with. We also have the constraints here, lambda 1 times x1 plus x2 minus 1 equal to 0, and lambda 2 x1 minus x2 minus 1 equal to 0. Now, this might look a little bit confusing. Why should these things be equal to 0? But it has a nice intuitive explanation. If we look at the actual area we're optimizing over here, now our two equations just form two straight lines. Now, the lambda 1 equation relates to this line here. So that is x2 is equal to minus x1 plus 1. So just if I change that equation a little to put x2 in front, x1 axis to the right, x2 axis to the top, and then the second line is x2 is equal to x1 minus 1. Now the given constraints tell us we're optimizing over this area I'm coloring in here, which of course extends to infinity to either side. Now the constraint of lambda 1 times the function g1, the fact that that product must be 0 means that either the solution will be found on this line or not. Now if the solution is found on this line, then x1 plus x2 minus 1 must be equal to 0. If the solution is not on that line, it is somewhere in here, and in that case lambda 1 will be equal to 0. The same with the one at the bottom. If the solution is on the actual line, x2 is equal to x1 minus 1, then x1 minus x2 minus 1 is equal to 0, and lambda 2 can be larger than 0. You can in a sense see these multipliers as an indication or a measure of whether our solution is away from the boundary of our convex region or not. So we know if they are both non-zero, that solution is going to have to be on the boundary. And if they're both non-zero, they're going to have to satisfy, or the optimal point is going to satisfy being on both of these lines. And the only point on both of those lines is their intersection there. But now let's see how this works in practice if we actually try to solve for our x1 and x2. Now the first thing to try usually, which is the simplest, usually, not always, is setting lambda 1 equal lambda 2 equal to 0. Now what does that mean? If we set lambda 1 equal to lambda 2 equal to 0, we see on top that there is no more lambda term in the partial derivatives of the Lagrangian. So we just need to solve for 2x1 minus 3 over 2 is equal to 0, and 4x2 minus a half to the third is equal to 0. So that's very easy. We get a quick solution. However, we know that we must check that our conditions corresponding to the function g1 and g2 are still satisfied. Now, the first condition is x1 plus x2 less than or equal to 1, but in this case, x1 plus x2 is 2, not less than or equal to 1. So we know this can't be a solution. Now for the next one, let's try lambda 1 not equal to 0, lambda 2 not equal to 0. Now, as I've said before, this implies that the solution must lie on the boundary of the region. Now, since we've drawn that, we can actually already see what the solution is, but we can also solve it algebraically, because all that means is x1 plus x2 minus 1 equal to 0, x1 minus x2 minus 1 is equal to 0, and that gives you x1 equal 1, x2 equal to 0, which is exactly the coordinates on the graph we found by looking at it geometrically or on the sketch. Now in this case, if you look at these solutions we've found, they satisfy all the constraints. x1 plus x2 is equal to 1, which is less than or equal to 1. x1 minus x2 is 1, which is less than or equal to 1. So we know this satisfies all the constraints. Now, are we sure this is the solution? Well, yes. If our Kuhn-Tucker sufficiency conditions hold. So it is vital when you solve a problem like this to check if the sufficiency conditions hold as well. Now in this case, today we're just going to look at the necessary conditions. We'll look at the sufficiency conditions in a later video. Now what if you found another solution? Let's see. What if you first tested lambda 1 not equal to 0, lambda 2 equal to 0? What if you found a solution there? Well, in this case, you actually can get another solution. By setting lambda 2 equal to 0 and looking at our equations, we get 2x1 minus 3 plus lambda 1 is equal to 0. We get 4x2 minus a half to the third plus lambda 1 equal to 0, and therefore lambda 1 is equal to 3 minus 2x1, and lambda 1 is equal to minus 4x2 minus a half to the power 3. Furthermore, we know from our conditions that if lambda 1 is not equal to 0, if we scroll up to our conditions here, lambda 1 is not equal to 0, then x1 plus x2 minus 1 must be equal to 0 if the product is to be 0. Of course, if you multiply two things and the product is 0, one of them has to be 0. So therefore, we have x1 is equal to 1 minus x2. Plugging this into x1 there, we get 3 minus 2, 1 minus x2 is equal to 1 plus 2x2, and that is equal to this term up here. So we get a fairly nasty looking equation. If we just bring the one term to the other side, 4x2 minus a half to the third plus 2x2 plus 1 equal to 0. Now you can either expand x2 minus a half here, but there's a slightly easier way to get to an easier equation. You keep x2 minus a half as it is, and you add another term, x2 minus a half there. Now you have to compensate for the extra number we put in there, which is minus 1, so I have to add 1. And now I set y equal to x2 minus a half, so our equation becomes 4y to the third plus 2y plus 2 is equal to 0. Now you can solve this quickly on the computer or on a programmable calculator and you get y is equal to minus 0.58975 approximately. Since y is equal to x2 minus a half, you just add a half and to get x2, so you get minus 0.08975, and solving for x1 is equal to 1 minus x2, we get 1,08975. Now if we look at this, unfortunately one of our conditions is x1 minus x2 is smaller than or equal to 1, but here we have 1,08975 minus, so plus 0.08975, and that is strictly larger than 1. So this solution does not satisfy our requirements. Now, to be clear, in the exam you do not need to solve for all the cases. For instance, there's one case we haven't considered yet, which is lambda 1 is equal to 0, lambda 2 not equal to 0. But once you have found the solution, as you've done in this part here, you do not need to continue if all the constraints are satisfied and the sufficiency conditions hold. The study guide and the textbook says that if the sufficiency conditions hold, the necessary conditions hold, and all the constraints are satisfied, then that is your solution. So although I used this part to illustrate the solving, you do not have to continue once you have found the correct solution. That is all for today. I'll see you guys again later.